Good morning, students. Today we are going to have yet another seminar class on Noether's theorem, which is going to be taken by one of my students, M. Ravi Kumar. He belongs to second MSc Physics in our college. Amy Noether from Germany. She lived between 1882 and 1933. So she lived around 53 years. She was a very famous mathematician. Jewish family, and his father was a mathematician and mathematics lecturer, and in fact father taught her all mathematics steps, earlyhood of her earlyhood child. But she liked only languages. She liked only French and German language. She wanted to teach only, as a teacher, she wanted to teach only language studies. So she studied very well during her school days. Then while coming to the college, she liked mathematics in fact. So she took mathematics and she started learning all mathematic skills from her dad. Then she became a professor in Erlangen University, where she was born. Erlangen University in Germany. For about 7 years, she did not get any pay. So without pay, she worked as a professor in the University of Erlangen University in Germany. Then in the year 1918, she published this paper which became very famous, Noether's theorem, which connects symmetry and conservation laws. Of course, whenever you find the physical system which is symmetry, surely it will go into conservation law, and vice versa. Wherever you find any conservation law for any physical system, that will have symmetry. So symmetry and conservation laws both will go hand in hand. Symmetry means any physical system, when you are going to transform any mathematical quantity like length, that will be preserved. That will not have changed. That will not change. So it's a preserved quantity. Conservation laws means already we know about conserving energy, conservation of momentum, and all those things. Any physical system which evolves with respect to time will not change. So she explained clearly about whenever you find any physical system which is symmetry, surely this will have conservation laws, and this has to oblige conservation laws, and vice versa. So she did a lot of works on mathematics. In fact, she was described by Albert Einstein that she was a very famous mathematician, famous woman in the history of mathematical physics. So such a wonderful mathematician. And in fact, in the year 1933, when Hitler regime came into the power, she was pulled out from Germany and she went to US, and she lived in the university in Pennsylvania for those days. And she produced a lot of doctoral students, and she did a lot of works on the theories of fields and rings. Her doctoral students also became very famous. So with this introduction about Noether's theorem, which connects symmetry and conservation law, and my student M. Ravi Kumar is going to explain on Noether's theorem now. So let us enjoy the seminar class. So now we invite M. Ravi Kumar to take the seminar class. Thank you.
Good morning to all. Myself M. Ravi Kumar, PG final year from Government Arts College, Melur. First of all, I would like to thank my head of the department, Dr.A. Jan Peter sir, to giving this wonderful opportunity to me. So thank you so much, sir. So my seminar topic is Noether's theorem. Let's move on the topic. Noether's theorem, named after mathematician M.E. Noether from Germany, illustrates the fundamental concept of quantum mechanics. Noether's theorem explains the three fundamental laws of motion. This is nothing but Newton's law of motion. Noether's theorem demonstrates the relationship between energy and matter, E equals mc square. Noether's theorem illustrates an intrinsic link between symmetries in physics and conservation laws. A symmetry is anything in which you have some sort of object and some sort of transformation. So we say that a system has a symmetry under a transform if the total energy of the object did not change. For example, translational symmetry, rotational symmetry, time symmetry, and so on. Noether's theorem asserts that to each continuous symmetry there corresponds a current, which we are going to discuss now, which satisfies a continuity equation, or equivalently a quantity which is conserved. Every continuous symmetry of the Lagrangian gives rise to a conserved current denoted as J mu of x, such that the equation of motion implies thus. This is nothing but equation of motion. We are going to use equation of continuity and conservation laws. This is equation 10.45. Here your J stands for current density. Symmetries under conserved currents are incredibly important in the field theory, and hence Noether's theorem is an invaluable tool for the field theoreticians. We know that the action in classical mechanics is the function of field and its derivative, and it is satisfied by the field equation. We know already this Lagrangian, which is the function of Lagrangian density, which is the function of psi, del psi, psi dot t. So they are all the derivatives, which is the equation of motion of fields with the following form. Euler-Lagrangian equation is given by this equation in the absence of time. So this is equation 10.46. The above equation is obtained by varying the action. Using Hamiltonian variation principle, the above equation is obtained. Let us consider a infinitesimal transformation of the field. Psi becomes psi plus del psi. This is equation 10.47. Accordingly, we see that this will be completely unaffected for any transformation which takes the form as exactly like this. Lagrangian also we have infinitesimal transformation, and similarly Lagrangian density also. So if it is to show psi implies psi plus del psi, your Lagrangian density becomes Lagrangian density plus df mu by dx, partial df mu by dx, and we are going to replace this partial is nothing but d mu. Your mu stands for covariant vector. We know already 1, 2, 3, 4. So d by dx is replaced by d mu. This Lagrangian density is written exactly like this. So this is equation 10.49, where f mu is some function of the field f of psi. If it is to show, then the equation of motion, equation 10.46 remains unchanged. So this remains unchanged. It is a symmetry if the Lagrangian changes by a total derivative del psi psi dot. This gives the change in the action of the general formers. We know that Lagrangian density depends on psi comma del psi. Then we have partial differentiation rule. Del L bar equals d L bar by the first one. So d psi del psi plus d L bar by the second one. Here del psi is nothing but psi dot. So del psi dot d psi dot del psi dot. This is equation 10.50. This equation 10.50 can be written as exactly like this. How to write this equation? Here del psi dot equals del, your psi dot is nothing but d psi by dx. So d psi by dx equals, your d by dx is replaced by d mu. So d mu del psi. And similarly d psi dot equals d, your psi dot is nothing but d psi by dx equals, your d by dx is replaced by d mu. So d mu psi. So this term can be replaced by this term, and this term can be replaced by this term. This is equation 10.51. I have written the same equation. First term of equation 10.51 satisfies the equation of motion. Hence using equation 10.46. This is equation 10.46. The first term of equation 10.54 is replaced by this expression. This expression is nothing but Euler-Lagrangian equation. So second term will be like this. This is equation 10.52. Using the product rule. Product rule is nothing but duv equals u dv plus v du. We know already. So we are going to differentiate this, keep this as constant, and we are going to differentiate this, keep this as constant. You will get this expression. See, we are going to differentiate this. Keep this as constant plus keep this as constant, and we are going to differentiate this. So this is equation 10.53. Now, if this transformation is a symmetry of the system, then we also have del L bar equals d mu f mu. This is equation 10.54. Using equation 10.53 and equation 10.54 we have. This is the expression of equation 10.53. This is the expression of equation 10.54. So comparing these two equations, we will have this expression. And bring this term to that side and taking the common terms out, you will get this expression. Your common term is nothing but d mu. This is equation 10.55. Whenever there is a continuous symmetry associated with the Lagrangian, then the quantity, the argument is nothing but either this term can be equal to 0 or this term can be equal to 0. This term cannot be equal to 0. So this term can be equal to 0. This is equation 10.56. This is termed as J mu. So this is termed as J mu. Hence the equation 10.56 becomes, so this is termed as J mu. So this equation 10.56 becomes d mu J mu equals 0. So d mu J mu equals 0. This is equation 10.57. Associated to every continuous symmetry, we have a conserved current. So this is our conserved current. Thus, we have proved Noether's theorem. This is a stronger result than saying we get a conserved charge. Indeed, a conserved current gives rise to a conserved charge. Thank you.